Hi, everyone. My name is Nishant. I'm a third-year PhD student with Dona Prikop. I'm interested in generally multi-step methods and then continual learning for my research. And today I'll be talking about multi-step methods and how GAE uses this idea to get state-of-the-art results. So before we get started, I put up like a Rich Sutton's quote from his RL book, which says TD learning has the as the most fundamental idea in reinforcement learning, and we'll see like why it is now. So outline for this talk will be, I'll first talk about TD learning, like how we get this TD learning update rule, and then I'll introduce end step and then lambda returns, and then I'll talk about TD lambda, which is like computationally efficient way of doing lambda returns. And then I'll talk about the view of TD lambda, which is temporal credit assignment, how we can relate TD lambda algorithm as a method solving temporal credit assignment efficiently. And finally, I'll talk about GAE, which uses many of the concepts and then ideas that I'll talk throughout as an advantage estimate in that work to get state-of-the-art performance on many control tasks. First things first, which is TD learning. So where does TD learning come from? So consider the policy evaluation setting where we are given a policy file. And our aim is to estimate the value function for this policy pi. So in other words, we have to compute b pi of s for all states s. This is the policy evaluation objective.
Sorry to interrupt you, but is your screen frozen or are you writing equations on your screen?
Yeah, I'm writing stuff on my screen.
Is anyone else able to see equations being written on the screen? Because it looks frozen to me right now.
No.
Okay, I'll try to reshare my screen again.
Okay, yeah, I see some update.
What about now?
Yes.
Can you see if
yes,
I scribble
see
something?
that update. Yes.
Okay, cool.
Awesome. Thanks.
Yeah, sorry for that. Yeah, I was saying like we have given a policy pi and we have to estimate b pi of s for all states. So typically what we do is we parameterize our estimates through a differentiable function. Let's say theta is our parameters. And we want to get close to b pi of s for all states s in s. Note that we can't kind of get exactly equal to here. That's because the parameters, the size of the parameters is very much smaller than the size of the total states. So essentially there are approximation errors in our estimates that we can't actually hope to minimize, but we can get closer to b pi of s depending upon how big our approximator is. So the way to go about this is stochastic gradient descent update rule, which is like very common in supervised learning. What the way SGD updates its parameters is we have theta t plus 1 that we want to get to, and we have theta t, which is the parameters at time step t. What we do is we take the mean squared error between the target and our predictions and minimize this error to get the update rule. So what it turns out to be is this one. I'm just like taking the gradient of this mean squared error. And what we would get is this guy. So this is what the update rule that we typically use in RL. We have v pi that we want to get to, and we have our estimates. We want to get close to v pi, and we take the gradient. This theta can be neural network for all we care about, or like deep neural network. So
there's a hand raised by Glenn.
yeah, Glenn.
I just had a short question, I guess. Did you describe like what V pi of S is? Like what that objective is a little bit more, and like how is it related to rewards?
Right. So V pi of S is the true value function of a state following policy pi. So we can probably write V pi of S as expectation over policy pi, and then summation of rewards starting from that state. So this is the definition of V pi of S. And essentially, this is the quantity that we want to get to, but then like we don't have access to this quantity because this is what we are estimating. That leads me to next slide, which is we don't have access to V pi, as I said, but then we want to estimate our values to get closer to V pi. So what we do is a solution for this is to use unbiased estimate UT as target. So our update rule would become same as before, but except in place of V pi of S, what we have is UT. And this UT can be RT plus 1 plus gamma V ST plus 1. This is what we typically use in TD0 or like TD learning rule. Note that this is not the true gradient, because if we were to take the mean squared error between our target, which is the one-step TD target, and our estimates and minimize, we get like two gradients, because our quantity here, which is the value of next state, is dependent on the parameters theta, and our estimate also depends on parameters theta. So essentially, we don't get the gradient only with respect to the estimate, but we get gradient with respect to the target as well as estimate. But in all the algorithms that we see, we typically consider that UT as a target, and we don't take gradient with respect to the target, and we only take gradient with respect to the estimate. So this is called semi-gradient rule, because we are taking only half gradient. It's like semi-gradient. So you might wonder, like, is TD0 target the only option to plug into the UT? Not necessarily. So we can also plug in Monte Carlo returns, which are typically denoted by GT, which are nothing but it's just like sum of discounted rewards that you would get throughout the trajectory. And then you can use this quantity as your target, and you can move your estimates to minimize the error between this quantity and your estimate. So this is another option. And there's like one more option, which is to use end step returns. So this picture kind of like captures the idea of end step returns. So you have this TD learning, which uses one step reward and the value of next state as a proxy for the remaining rewards. And you have this Monte Carlo methods, which uses all the rewards that it sees throughout the trajectory until the termination as a target. And in fact, you can kind of like go anywhere in between TD learning and Monte Carlo learning. So by varying how deep you want to go, you kind of control how much rewards you want to accumulate, and then what value you have to use to as a proxy for the rest of the approximations. And this picture also kind of like relates TD learning to dynamic programming and exhaust research. So if you see TD learning, it only goes like across depth. So you go across depth 1, and then you bootstrap from there. But dynamic programming algorithms, they kind of like are breadth first sort of a thing, in the sense that they take all the possible states that you can visit in one step, and they bootstrap from there. So DP targets could also be used for UT. And what are these methods that kind of like fall between temporal difference learning and then Monte Carlo learning? These are called end step returns. So the idea, as I said, it's like you collect rewards as you go, and then you use the value of the state at the end of a particular point as a proxy for the remaining rewards from that point onwards. So you have this TD0 as a backup diagram, which uses one reward and value of next state. And then you have two-step TD, which uses two rewards, and then the value of the state after two time steps as a proxy for the target. And similarly, you can use three-step and n-step and so on. And if you kind of like extend it to infinitely many rewards, you'll recover the Monte Carlo estimates or Monte Carlo returns. I'm just like rewriting this n-step returns mathematically here. So you have like one reward and the value of next state in one-step return. Similarly, in two-step returns, you have two rewards and the value of the state after two time steps as the target. And similarly, you can have like three steps and then n-step rewards. So why do we need n-step returns is a question that you might be asking right now. So we know that TD0 uses only one reward, and for the rest of the things, it uses value estimate. So our value estimate might not be like a correct quantity, in the sense that the approximation error of our target state would be pretty high. But even though the approximation error is high for our target state, we still use its value as our target for the current state. As a result, errors also kind of get backed up in our update rule. So this might cause bias. And on the other hand, we can avoid this bias by considering many reward functions, many rewards, as is the case in Monte Carlo returns. But then since rewards are stochastic and then the trajectories themselves are stochastic, variance could be really high. So it's really the problem of bias and variance. So if we kind of like increase n, we are getting higher and higher variance in our target, but we are reducing the bias. But if we take smaller and smaller n, then we are getting higher and higher bias, but we are reducing the variance. So optimal n depends on the problem that you have in hand, and also it's a hyperparameter for the learning rule itself. Okay, going forward. So there's this concept called forward view, in which is if you see n-step returns, you don't immediately get access to all the rewards when you are in state ST. So agent has to take action according to policy pi, and then it sees like one reward, and then it has to take another action from the next state to get next reward, and so on. So if you're using like three-step returns, for example, as your target, agent has to wait 3 time steps to actually compute the return or like target for the state, which is 3 time steps back. So this is kind of like captured in the slide that I'm showing right now, which is forward view. So agent has to look forward in time to see what the rewards and values are to actually compute the target. So this is forward view. And n-step returns are not the only options for us to use for UT. So there's something else called lambda returns. So what are lambda returns? So basically, they are just like a mixture of different n-step returns. You have one-step return, and you have two-step returns, and you have three-step returns, and so on. So what you do is you take like averaging of all of them. So a simplest way could be you can kind of like have a weight of 1 by n for all the n-step returns that you are considering. That is also a valid target. And another way which lambda returns does is like a convex combination of all the n-step returns. So here, convex combination is controlled by the parameter called lambda. So that's why we call it lambda returns. So mathematically, what we do here is we take one-step return, which is GT1, and we we multiply it by the weight 1 minus lambda, and we take two-step returns and multiply it with 1 minus lambda times lambda, and we have three-step returns, we take 1 minus lambda times lambda square and so on. And we sum up all these returns. So essentially what we get is like mixture of all n-step returns. So why do we want to do this? As I mentioned before, uh, an optimal n depends on the problem in hand, and then it's a hyperparameter tuning. So for a particular problem, you might not be able to know which n leads to the best solution in advance. So what you can instead do is you can take mixture of all the n-step returns and then transfer the problem of choosing optimal n into lambda. Now, by choosing a different value for lambda, you're kind of like mixing different n-step returns differently. So if lambda is 0, you fall back to the case where you have only one time step target. And if your lambda is 1, you have a Monte Carlo target. So you're collecting all the rewards before you compute the target. As like n-step returns, even lambda returns requires waiting because it depends to compute the target. You'll have to wait until you have observed all the rewards and all the states to actually compute the target. So this is again, you can think of it from the forward viewpoint of view, where agent sits at time step the state at time step t, and then it has to wait until it sees all the rewards in future to actually update the value of state at time step t. So you can also control bias and variance here by choosing lambda. If lambda is set to 1, you fall back to Monte Carlo return case where there's very high variance and 0 bias. And if you kind of set lambda to 0, you are in TD0 case where you have very high bias, but then very low variance. So depending upon how you set lambda, you kind of like are intermixing different n-step returns, thereby controlling the bias variance trade-off. So the higher the lambda, the higher the variance. Yes, Glenn?
So I guess maybe from your background or experience, like what is a good value to set for lambda then when using a method like this?
Actually, there's no one good value. It depends on the problem that you have. So typically, what we observe usually is intermediate values of lambda works better than either of the extremes. So for some problems, it could be 0.4, for some it could be 0.6, or for some it could be 0.8 or 0.9. But then if you go beyond 0.9, then you might have a problem of high variance. Then if you kind of like reduce it by too much, then you have a problem of high bias. Even theoretically, your fixed point, how close you are to the true value, which is v pi of s, depends on the lambda that you set. So the higher lambda that you set, the closer you would get to v pi. But then the ball of convergence is like very huge because the variance is very high in the returns. But if you kind of like set lambda to 0, then you would converge like really quickly. But then there's very high bias which can't be minimized even if I give you many more samples. Yeah, Rishabh?
Is there some issue with the formula? Because if I put lambda equal to 0, I get 0 as the GD lambda. And if I put 1, then it seems undefined. Like, was it an inverse? Of 1 minus, I think it's an inverse because you're normalizing the reading. So it's 1 minus lambda inverse, I think, but not sure.
So give me a second. Yeah, I'll have to think. I'll have to check and come back to it later. Maybe there is some error. I don't know. Where I'll fix it if there is something. Thanks, Rishabh. Yeah, Gandharv.
Yeah, so I always have this question about TD and in general how we evaluate algorithms. Now we have all of these literature, this huge literature on how we evaluate algorithms, and particularly this talk of bias and variance. Yet when we actually evaluate algorithms, when we actually run whatever we want to run, and when we check, we always do Monte Carlo evaluation.
What do you mean by we always do Monte Carlo evaluation?
I mean, when you run a particular algorithm, and so whatever plots we have in our papers, those are not, that is not the TD estimate, right? That's just the Monte Carlo estimate of your value. Let's say if you're starting in a continuous environment, and if you're running, for that matter, even if you're running a policy-based method, you just start accumulating your results from the start, and you just display those. And then you check, okay, if method A is doing better than method B.
Right.
And in many ways, that is also the value of your policy. But we don't do TD there. We always do Monte Carlo. So I always there's this confusion in my head as to what. Yeah, and even though it is even though it is multiple episodes, it's still Monte Carlo, right? We are not.
Yeah. So I think what you're getting at is the main objective of RL, which is to maximize the expected reward, right? So that's what we want to measure our agents with. But then how we maximize it is through the methods of temporal difference learning, or Q-learning, or SAS, or policy gradient. So, I mean, you can use any method that you want to, but our end goal is to get to the optimal policy and to measure expected discounted rewards or expected returns without discounting. So that's what I think you're commenting, right?
Yeah, no. So what it's unclear to me is how, let's say how does the bias and variance, that is happening within your TD affect that performance which we actually compare?
Right. So let's say your value function, let's say there's very high bias in your estimates, which means you're very far away from the fixed point V pi. And even if I throw you millions of samples, you can't minimize that error because that's coming from bias. Now, what happens is an agent which tries to come up with a greedy policy using these estimates, or if you want to do policy improvement using these values, then the policy that you would get may not be really good. It might be
we never
very
use
bad.
greedy policies, right? We always use exploratory policies. There's always some exploration, be it policy based or be it value based.
Right. Even if you use exploration, or if I give you infinite amount of data, there's bias that can't be reduced, right? And that could affect your performance because your values are not good. As a result, the policy that you get is not good. As a result, the expected returns that you would get is also not good. So the better values you have, then better policies that you can get to, and then better performance that you can get to. So this kind of this idea is summarized in GPI, which is generalized policy improvement, in the sense that you have this V pi, and then you go to pi, and from pi you get another V pi, and then from another V pi you go to the next pi. So for this cycle to be fruitful, you want your estimates to be good. Otherwise, your policy may not be good.
Okay. Yeah, I haven't seen this. I'll go through GPI carefully again. But yeah, thanks.
Yeah, Hardy.
When n is equal to 1, it will return GP1.
I'm not able to hear you, Hardy.
You're very quiet.
About now?
Yeah, you're better now.
So, regarding the previous question, I think even when lambda is 0, for n equal to 1, it will still return G1t, right? Which is correct. So I think the formula is correct.
Oh, I see. Okay. Thanks. But I'll have to check, Rishabh pointed it out. Maybe there's some error, maybe there isn't. I don't know. I'm not able to think clearly in the heat of the moment.
Yeah,
sure.
I wasn't sure about lambda equal to 1 actually. That's 0 because of the multiplication.
Yeah, but for n equal to 1, still it will return G1t.
Typically, what I'm used to seeing for lambda returns is there are two terms. One is this, which goes up to n steps. And then there's a residual term, which has this lambda to the power the next part for the, which runs for the following steps and for which it is the GT. So that's where it balances off. That's what I'm used to saying.
Right. So for this talk, let's kind of like simplify. Let's not look at this equation for now, and let's kind of like think of this diagram. So what we have is GT lambda, which is nothing but convex combination of different returns, right? So let's just take that. GT3 and so on. So whether this simplifies to this particular formula, maybe I don't know, but like for now, like let's consider this one. Cool. So as I said, like Lambda returns requires you to wait until the end of the episode for you to get rewards so that you can update your state seen in the past. But there's like a smart way that we can do to get around this problem. And this problem is actually very problematic in non-episodic setting or continuing problems where there is no termination, because agent would keep collecting rewards and values, and then it never gets a chance to update the values of the state seen in the past. So we want another way where we can kind of like compute Lambda returns, but then we don't have to wait. As with anything, like we can do a bit of math to find a solution, and which is what I'll be doing like now. So let's start with Lambda returns, which is GT lambda. Which is like just convex combination of different returns, different n-step returns. What I'll do next is I'm gonna expand each of these returns as a sum of rewards and then value function. So by the way, like most of the math that I'll be doing now will be used in GAE paper as well. So I'm gonna kind of like skip it when I'll be talking about GAE. So I'll go in detail here. I'm just like rewriting the different returns as sum of rewards and value of the states. And so on. Next, what I'll do is I'll try to separate the rewards terms and I'll separate the value terms. So we have 1 minus lambda times RT plus 1 coming from here. One minus times lambda RT plus 1 and comma RT plus 2 coming from the second time step. Plus so on. These are the reward terms. And for value terms, we have 1 minus lambda times value of ST plus 1, 1 minus lambda times lambda multiplied by value of state at ST plus 2, and so on. Now what I'm going to do is I'm going to group these rewards in a different manner. So what I'll do is I'll collect all the RT+1 rewards first and then group them together. I'll collect all the RT+2 rewards and then group them together, and RT+3 rewards and group them together. So what I have is I have 1 minus lambda RT+1 times I have 1 here, and I have lambda here, and lambda square here, and so on. Similarly, I can do it for RT+2. And I'll also have the value terms here. So in the next step, what I'll do is I'll try to simplify this summation, which would just be 1 by 1 minus lambda, and then try to rewrite the reward terms. So what I'll have is 1 minus lambda RT+1 or 1 minus lambda plus gamma lambda times 1 minus lambda RT+2 or 1 minus lambda plus gamma lambda square 1 minus lambda RT+3 or 1 minus lambda, and so on. So essentially what we have from the reward terms is RT+1 plus gamma lambda RT+2 plus gamma lambda square RT+3, and so on. And I'll also like rewrite the value terms that we left before, which is one minus lambda gamma VST+1 gamma square lambda times 1 minus lambda VST+2 and so on. Now what I'll do is I'll try to rewrite these lambda returns in terms of TD errors, because what I have is I have reward, I have like value of the next state, and then with a bit of simplification, I can kind of write these terms as deltas, where deltas being like TD error. So next, what I'll do is I'll add and subtract values of each and every state throughout this sum to get like different things. So I'll add and subtract V of ST here, and add and subtract V of ST+1 here, and then add and subtract VST+2 here, and so on. So what I would have is This is what I'm adding and subtracting for the first term. And then I can continue doing this for all the terms that I have in my summation. So if I kind of like write it as TD error, what I would get is get gamma times VST plus 1 minus V of ST. So I'm taking this term and then gamma times this term. And this would be equal to one step TD error, which is delta T. And for the next one, what I have is RT plus 2 plus again, for the next one, what I'll do is I'll take gamma times VST plus 2 and keep the other term separate. Now, what I'll do is I have this minus gamma lambda times VST plus 1 that I haven't used before, which I'll be writing here. This is equal to delta T plus 1. And what we would get is by doing this delta T plus 2 and so on. So essentially what we have done is we had lambda returns and we group reward terms together and then we group value terms together and we are writing lambda returns as sum of TD errors. So essentially what we can do is GT lambda plus V of ST because we can't group V of ST term anywhere, but all the other terms get cancelled. Plus V of ST is nothing but so let's just say yeah. So this is what we would get like by grouping all the terms. Oh, this is actually minus. So once we have this, if you remember the update rule that we have, so WT plus 1 would get to WT plus alpha UT minus V of ST times gradient of V of ST. So we can substitute, instead of UT, we can substitute G lambda, which would be this entire term plus V of ST. So essentially what this expression means is that we are collecting TD errors at different points in time, and we are discounting it through gamma lambda, and we are kind of like updating our weights to minimize the discounted sum of TD errors. That's what this expression means. But again, like as I said, like our main objective is to get rid of waiting time because we want to be able to update our estimates in an online fashion. So instead of waiting until this estimate, we get all the TD errors, what we can instead do is we can update our weights at time step T using just the TD error that we receive at that time step. And during the next time step, which is T plus 1, we can update our weights using the gradient and the TD error of that term And we can also add gradient of V of st. Essentially, what's happening here is that we have accumulated, or we want to minimize the sum of TD errors and take the gradient of our value of state st. But we don't have access to all TD errors at time step t. We have access to only one TD error. What we'll do is we'll update the our estimates using the TD error that we have at that point in time. And at the next time step, we have TD error at that time step, which we use it to minimize the value of state st plus 1. And we also use the TD error to minimize the value of state at V of st. So essentially, at every point in time, we try to kind of like minimize the, we kind of try to pass the TD error to all the terms that we have. Sorry, there has to be gamma lambda here, coming from here. So in fact, like if you see here, we are using our gradient that we computed at time step t of our value over and over again. Instead of like recomputing it at every point in time, what we can do is we can accumulate this term in a particular memory, and then we can use that memory whenever we need it. We can put this guy in memory, and we call this memory ET, which is nothing but eligibility traces. So what the update rule looks like is where ET is nothing but gradient of the value function of the state, and it's gamma lambda discounted term. So this way, what we got is we kind of like rewrote lambda returns as sum of TD errors. And then we say, like, instead of updating TD error, waiting to get all the TD errors, we update when, if and when we receive this TD error, and we store the gradient in our eligibility traces. And we use this eligibility traces to update our weights. So this is the idea behind the algorithm TD lambda. And since both lambda returns, which is forward view, is equal to this guy, which is backward view. I'll tell you in a bit why it's called backward view. So there's this equivalence between these two algorithms, lambda returns and TD lambda, and it's called forward backward equivalence. I see a lot of items in the chat. Like if there's like a quick 1 or 2 questions, I can probably answer, or I'll move forward.
It seems like the stuff in chat is a discussion about the bias and variance of like whatchamacallit, Monte Carlo methods.
Right. Got it.
Yeah.
So I can move forward in that case. Yeah, so what's happening in TD lambda is that we have error at time step t, and we are shouting it back to all the states that we have seen in the past, but by discounting through gamma lambda factor each time step. So the state that is one time step away from the current time step will get like gamma lambda times delta as the update, and so on. It gets like smaller and smaller TD error as the state is further back in time. So that's why we call this like a backward view. And this backward view kind of like gives us the, it was first, eligibility traces was first designed to be like computationally equivalent method and efficient method for lambda returns. But over the period of time, like we are seeing these traces as a mechanism to do temporal credit assignment in RL. Like, why is that so? If you see the update equation here, we have our traces which has the gradient at time step t, and we have the error at time step t. So essentially we are asking the question, well, I have some error at this point in time, which is delta t. Which state should I pass this error to? Should I just update my current state, which is V of st, or should I pass it to all the states that I have seen in the past? And the way we can control it is by adjusting lambda. So if we set lambda to 0, then we are putting all the blame or all the credit to the current state. But if we set lambda equal to 1, then we are saying, well, all the states in the past were equally responsible. But for any other lambda value, we have like exponentially decaying way of credit assignment using these eligibility traces. So in a way, this idea is similar to real-time recurrent learning in RNNs and LSTMs. So what they do is also, instead of doing backprop through time at each and every point in time, they accumulate the gradients of the states that they have seen, and then they kind of like pass or like update the weights through this accumulated gradient quantity. So in a way, eligibility traces are also doing a similar thing here. Eligibility traces have accumulated the gradients, and then we update the weights through this accumulated gradient. So one, there are like a couple of research ideas that comes to my mind here. Like one is connection with backprop through time. So as I said, like this is the idea is very similar to real-time recurrent learning, and there is a connection between, there could be a connection between backprop through time as well. And this hasn't formally been exploited in any of the works. So there are like a couple of works which mentions that this is similar to real-time recurrent learning, or this is similar to backprop through time, but there's no mathematical or like experimental connections or like evidence established formally in any of the papers. And another idea is with connections with optimizers. So if you think of momentum SGD or Adam or Adagrad or any of those sort of optimizers, they are accumulating gradients, and then they use this accumulated gradient to update the parameters, which is what is happening here as well. So maybe there's like some formal connection that could be made from optimizer's point of view. So that's another idea that I can think of. Yeah, Gandharv?
Yeah, so I just had a question about the first idea that you were speaking about when you were saying recurrent learning. So the way I think about it, what you're doing essentially, what you do in, but what we do in deep learning is you have your features, right? And then you use your features, and your features are basically you put it through a feed forward layer, and then you get your value estimate. Correct.
Mm-hmm.
So when you're going to use neural network, and if you're using a recurrent neural network, what you would be essentially doing is using history-based features.
Right.
So yes, that's what. So when you said that you want to establish the connection between between using history-based features for learning value estimates, is that what?
Yeah.
Okay.
Yeah, I see your question. So basically, what Gandharv is saying, if you consider feed-forward neural network, there is no backprop through time that people do in supervised learning. But if we consider feed-forward neural network to get our features and to get our value estimates, we can still do backprop through time, is my claim, in the sense that we have this gradient quantity that we are accumulating even in feed-forward network. And even for a single feed-forward network, we could do backprop through time sort of a thing. But if you have like a complex system to get features like a recurrent neural networks, then there would be two backprop through times that would be going into that network. One is because your features are history-based features, and second one, you're using traces to update your weights, which themselves have history of gradients in them. So these are the two ideas that Gandharv was saying. Hadi, like, do you have a question as well?
No, it's clear. Thanks.
Okay. Yeah, and the third idea that I could think of is what we worked on like recently, which is called preferential TD learning. And here, like, if you see eligibility traces, there's exponential decay of credit for all the states seen in the past. So if you think of actual temporal credit assignment problem, whenever you see error, you either assign it to a particular state or like few states in the past. But here, what's happening in eligibility traces is that you are exponentially decaying your credit and you're assigning it to all the states seen in the past. But what we do here is like provide a mechanism where you can skip certain states in between and then assign the credit directly from one state to another state, which are like temporally very far to each other. So that's another idea that can be exploited further, because in our paper, we kind of assume that these betas are given where you know which state to from which state the credit should be passed to which another state. But most interesting scenarios come when we have to learn these credit assignment states, like where you have a source state which requires credit, and you have like another state which passes the credit. So how do you identify these two states, the causally related states, and how do you pass the credit from between these two states? That's an interesting direction as well. Well, like where does all these ideas lead to? Like one paper that I can think of is like generalized advantage estimate. So essentially, this paper like talks about like a policy gradient methods, and they introduce something called generalized advantage estimate, which is nothing but like a gamma lambda combination of, or like convex combination of different TD errors, as we'll see now. So before we get there, like I want to quickly like point out the motivation here. So what they're saying is there are like two challenges in policy gradient methods. One is they require large samples, and then the other is that they don't have steady improvement because of non-stationarity. So large samples is because of temporal credit assignment and variance in the updates, and steady state there's no steady improvement. That's because your policy is continuously changing. Agent is visiting new states. As a result, there is non-stationarity, and then there's no consistent improvement. What they try to do is like they try to solve this first problem using something called generalized advantage estimate, and then they solve the second method using trust region optimization techniques. So I'll just be talking about first point. Before that, like I'll just quickly give like overview of like what those methods are. So typically what we want to do is we want to maximize like our objective function in policy gradient is sum of discounted sum of rewards starting from a particular state. And this particular objective can take many different forms. And equation one kind of like gives like a very general form, which kind of covers all the different forms that you would see. For example, you can compute, you can replace psi with sum of rewards to get like reinforced, and we can replace this guy psi with returns minus baseline to get like baseline version of reinforced. Or you can use advantage function, or you can use TD errors, or you can use Q value. So you can use like many different terms that you want. But typically what this paper claims is that using advantage function is better, because many literatures have observed that there's like a reduction in variance by using that. So this paper like defines like advantage estimate, but like a generalized version of that. So advantage estimate is usually like a one-step TD error, but what this paper does is like you can also consider like two-step TD errors, which is one-step TD error plus discounted TD error at the next time step. And similarly, you have like three-step advantage estimate, and you also have like n-step advantage estimate, which is nothing but gamma discounted TD errors. In fact, as I said in lambda returns, like you can also take like convex combination of these different advantage estimates, which is what they do in GAE gamma lambda, which is nothing but they take this convex combination of different advantage estimates. So I can quickly write the math or like go through the math from the paper. So I think like in the interest of time, I'll just like briefly tell you what's happening here in the advantage estimate. Just a second. Yeah, you guys can see my screen, right? Where I'm sharing a paper. Yeah, essentially what this paper does is like introduces this generalized advantage estimate, which is convex combination of all n-step advantage estimates, which is nothing but convex combination of TD errors as we've seen in lambda returns. So here we have, we can group again lambdas together here, like one-step TD errors together, and then compute the coefficient that they have. we have second time step TD error and corresponding coefficients and so on. Upon simplifying these coefficients, what we get is we get like a gamma lambda discounted sum of TD errors. So this term is what they're calling it, calling as generalized advantage estimate. And in place of psi, that's what they use. So you have this gradient of log probability of taking an action, and you multiply psi to it. And psi here is nothing but your generalized advantage estimate, which is given in equation number 19. So they observe like state-of-the-art performance in many different games by using this technique, along with trust region policy optimization. So I won't be able to cover this trust region ideas, but like if you have any questions on GAEs or like lambda returns or how they can be seen together, like you can ask me now. Movis, looks like there are no questions. So I think that's it from my end.
Yeah. All right. Well, let's thank Nishant for presenting to us today. Yeah. Okay. So next week we will have. Let me get this up. So next week on Tuesday the 8th, we will have Andrea Driak. I don't know if I'm saying their last name correctly. We'll have them present next week, and the paper they will be presenting is to be determined. So I'll be sure to message them right after this meeting is over. And yeah, thanks for attending this meeting.